Hello and welcome back. Firstly, thank you everybody for your very positive comments on the last video and subscriptions. I've still been amazed by the response I've had to these so far, so thank you very much for that. In this video I'm going to continue with the work on machining the two flywheels, and starting with machining this relief where the big end eye sits inside the flywheels. The most important dimension is actually the depth of this counterbore, which I'll explain in a little bit more detail in a minute. In conjunction with that, I'll also be checking out the distance between the inside of the main bearings on this pair of cases, because effectively the depth of this counterbore and the width of the flywheels is all part of the stack up that gives the final dimension between the two faces where the bearings sit, and therefore the actual end float of the crankshaft within the cases. And obviously what I don't want to happen is the dimension across the crankshaft to be larger than that of the distance between the two bearings. Once that's done, hopefully in this episode as well, I'll be doing a little bit of CAD work looking at the drilling of the oilways in the flywheel on the timing side. Thank you. My first job is going to be getting the depth of this counterbore that gives our clearance to the big end. I'll use a depth mic, just get a nice accurate measurement, just check the zero on a surface plate. Yep, that's good. And again, make sure that's sitting down nicely, and let's get a measurement. And that is 2.68 millimeters. 2.68 millimeter counter bore depth. Next thing I'll do is just get the diameter of this counterbore. It's just a clearance and actually runs out into a chamfer, so a vernier measurement is fine for that. And we've got 49.55 millimeters. 49.55 counter bore diameter. Then finally, let's just check the angle of that counterbore. So, down there, excuse me if I'm getting in the way, and that is almost exactly 45 degrees. Don't know how well you can see that, but hopefully okay. 45 degrees. So that's all the information we need from that. the next bit of data to collect is the distance between the inside races of the two main bearings. So I've got a pair of crankcases that I've assembled up and bolted up in a couple of places, and I can just go in with a internal micrometer and catch that dimension. Again, hopefully I'm not getting in the way. A bit fiddly. That's pretty good, and I've got 2 inches and 2 thou. That's about 50.9 millimeters. So from that data and a measurement across the crank pin here, I'll check it with a micrometer just to make sure in a moment, I can work out the stack up of the assembled flywheels, the crank pin, and then get the dimension across the 2 flywheels where it'll sit inside the cases. Having done my various sums and bits and pieces, it actually works out that I need to go a little bit deeper than this particular flywheel measurement, nearer 2.9 millimeters rather than the 2.67, to ensure that effectively I don't get an interference fit between these inner races when the whole crankshaft is assembled. I suppose it doesn't particularly surprise me the number of these different cases I've measured when doing various machining ops or building engines. I do find quite a large discrepancy between measurements, and you do have to be very careful just trying to, if you're measuring one part and duplicating it, doesn't necessarily give you the result you might expect. But yeah, often found with these various trike bits and pieces. Here's the lathe faceplate, and we've got to get the flywheel on here with the big end bore central to the faceplate. I'll get it properly trued up on the lathe itself, but I'll get a 2 or 3 good clamps on this, get it roughly positioned, then we'll get it on the lathe. It's going to be one of those jobs where the setting up is going to take 3 times the time of the actual machining operation, but that's not unusual when doing this sort of thing. Right, I've got 3 decent sets of clamps on this. It roughly centered by eye at the moment, so let's get this on the lathe and get it trued up nicely, then we can start cutting metal. So I've got the faceplate on the lathe and centered the bore up approximately, just using a center in the tailstock just here. I've also added a big old steel parallel here just to act as a counterbalance, because this whole thing was well and truly out of balance with the massive flywheel over here. And we've got about 4 or 5 thou run out there. Just see if we can get that a little better, and then we'll get on with the facing operation. So I will just see if I can bring that over a little. About 3. Nope, got worse. That's better. We've got a couple of thou on that now, which effectively we're just doing the counterbore to add clearance. So I'm going to tighten up, happy enough with that. So just make sure all these bolts are well and truly tight, and we can get on with some machining. There's not a huge cutting force on this, so shouldn't have any issues. Just slackening this one to start with, because these two blocks aren't sitting real. That's better. Now tighten up again. And there we are, with a couple of thou run out. That's fine for what we're doing. Here we go then, it's time to actually start cutting some metal. So let's get things going and see how we get on. For a cut of about 1.5 millimeters. See what that looks like. I've set the DRO to give actual sizes. Right, this will take quite some time, so I will switch off and bring it back when we're a bit nearer. That's the first cut done. Finish looks pretty good. Let's see where we are size wise. The cut was intended to be 1.5 millimeters. So hopefully I'm not too in the way. Let's see where we are. .6. That's not too bad. So I'll take another millimetre off of that, and then that'll just give us a fairly small last cut. help if we go the right way. There we go, cutting again. I've bored our recess now. The last operation in this setup for this flywheel, I'm just going to put a chamfer on the crank pin bore, because the crank pin's ground. There's going to be a radius between the shoulder and the shaft, and we'll need a chamfer to clear that. Try and zoom you in. And there we go. Don't know if that'll stay in focus, but no, looks like losing it. There we go. All done. Just got to repeat it all on the other flywheel. I'm now thinking about machining the oilways in the flywheel, and to start off with, I'm back on the CAD to work out the best positions of the oilways and end up with a dimension drawing to do that. So what you can see on screen at the moment is a abbreviation of part of the crankcase, stub shaft, one of the flywheels and the bearing assembly. But for what we need to do, I'll switch a few things off because we don't really need them. We'll lose that. We'll lose the stub shaft, approximation of the gears, and that now just leaves us with the flywheel. For those that are interested, this CAD package is AutoCAD Fusion 360. It's really a very good solid modelling package that I've used for a couple of years now. It's actually free for non-commercial use, which is really good. There's very few limitations. You can only have 10 parts or assemblies or drawings going at once, but you can archive things and bring them back. So it's a really useful tool, and this is something I've taught myself to use, although I've used various CAD over my working career. Never really had any formal training. Most I've picked up myself, and I believe anybody who's got the skills to take an engine apart and put it back together could potentially pick up a package like this and get to be able to produce parts, assemblies and everything else. Anyway, so let's get on. What I'll do is I will switch on a cross section through the flywheel, just spin that round, and let's have a little look at that now. So here's a cross section through the flywheel, through a plane that's where the oil drillings would go, and got the main shaft bore here and the big end bore there pitched out, and what I've done is created the drillings for the oil to get from the main shaft up to the big end. The reason why there's two drillings is for the sludge trap to be effective. If you just brought the oil in at the centre here and went straight up to feed the big end, those heavier particles in the oil, bits of steel, contamination, etc., that you want centrifugal force to drive them towards the sludge trap. If you bring that all in on centre and don't take it away from the big end first of all, approximately 50% of the heavier contaminants will go straight up to the big end. And if you had a sludge trap oppositely opposed down here, about 50% of those particles will go to that sludge trap. So if you look in detail at the early crankshafts with the tapered bore in the boss, the oil is directed initially away from the big end and towards the sludge trap. So really you want the oil to come in initially to be directed away from the big end, so centrifugal force will then continue taking these particles down to where you've got your sludge trap, and the oil with those particles separated out will then go back up to the big end, and that's the principle on all these centrifugal separators that are trying to get particles out of the oil. It means more drilling and longer drillings, but yeah, I think that's necessary. This is a schematic from the Haynes manual of the plain main bearing engine, and what you can see is the oil is fed in, then directed down towards the sludge trap where the heavier particles will then separate and go downward, and then the cleaner oil comes up and feeds the big end. Interestingly, this is a drawing from the Bible which shows the later type twin bearing engine, and here the oil is coming in central to the shaft, and there appears to be no attempt to initially direct it towards the sludge trap, but I haven't actually seen a crankshaft with this configuration. On the later ones I've experienced, there is drillings that initially take the oil towards the sludge trap and then back beyond the crankshaft centre line up to the big end bearing. So just something that's interesting there. So having modelled this, I will produce a drawing from that. I've ordered some long series 4mm drills to be able to drill these long passageways. I'm going to use a 5/16 UNF thread and make plugs to suit to blank the ends of the sludge trap area. So going to get on and produce a drawing. So I've got a nice bit of paper with all the necessary dims on, so when I get to setting up on the milling machine, I've got something good to work to. I'm just going to show you a little bit of the CAD package creating a drawing, just out of interest, to give you a flavour of how that's done. Right. I have this main view in here. What I'll do is create a side view. And from that I can create a section view to show the oilway drilling. And then I'll be able to start dimensioning all these oilways with reference to the two bores that I've got there. And let's just save that so it doesn't disappear if the computer crashes. That'll need a little bit of neatening up, but now I believe that's all the principal dimensions I need to go away and be able to machine the two oilways. I need to thank my mate Joe, who's also building tiger cubs at the moment, because whilst I was doing all this work on oilways, he actually stripped down a later twin bearing crank and sent me a few pictures which finally answered my queries about the exact nature of the sludge trap and the drillings. I've put a couple of these up just as stills, just for interest for you guys. What you can see is Triumph actually fitted a considerably larger sludge trap into the flywheel, and then did a sort of cross drilling at a compound angle to connect this to the feed through the main shaft. I'm not going to do exactly this just because of the complex nature of that compound angle drilling. It's easier for me to do the two holes I've shown on the CAD, so I'll proceed in that manner. It means the sludge traps that I will have are going to be slightly smaller, but I'm not anticipating a bike that's going to be doing many thousands of miles. This is a trials bike, so I think a smaller sludge trap isn't going to be an issue, particularly that with me fitting an external oil filter as well. Starting now to set up to drill the oilways through this flywheel. What I've got here on the mill is a dividing head. It allows you to rotate things at very fine angles or index them through almost an infinite number of different indexes. So what I've done here so far is I've made another little split mandrel which I'm going to mount the main shaft bore on, and then I can start positioning things to start drilling. First job I've got to do though is just centre the spindle of the machine on the axis of this mandrel. So I do that using a clock again. Basically bring it down onto the shaft, finding the lowest point, zeroing that, rotating a little till again find the lowest point and bring it up and over, doing the same on the other side. And when both sides are hitting zero, which they are at the moment, the spindle of the machine is on the centre. So I'll zero my digital readouts and also just set the mechanical dials at a convenient point as well, just in case I lose the digital readout at all. Just checking that. So that's all good to go. So next job, get the flywheel mounted up and start positioning for the first bit of drilling. Next part of the setup is to get the main shaft bore and the big end bore dead horizontal. So we've got a reference between the two. So I've built up some slip gauges just to fit under the split mandrel. So that's the bottom of the main shaft bore. I've zeroed my clock on that. Then I'm going to come over to the crank bore, which actually is slightly bigger in diameter by 1/28 thou. So it's going to sit a bit lower and just get contact on that till the bottom of that bore is 14 thou lower, which I've got there. Now I can tighten up this mandrel. Oh, move my clock, but we can check everything. So that's solid apart from playing the dividing head, which we're not going to worry about for the moment. So that's on 0, and that is 12 thou, 12 to 14 thou lower. We'll just tweak that a bit. That's it. So now we're 13 to 15 thou depending where that play is, but we can deal with that play on the dividing head in a minute. So now we know these bores are dead level. A quick cross check will be to rotate this part 180 degrees and we should get exactly the same reading when the bore's over here. So we'll do that just to check things out. Just move my slip gauges. Index that round. Come round, right. Come round over here. And there we go. We are at 10 thou. So we can improve that slightly. Can undo that. Split the difference, go to about 12. Move it back the other way. That took a bit more mucking around than I expected, but now we have 0 on that side. And if we spin it round, nearest damage 0 on that side. So happy enough with that. This device here, known affectionately as a wobbler, helps you find a edge exactly. This little barrel shaped portion at the end is exactly 4mm diameter, and when I wind in it'll true itself up, and the moment it skates off is when you're exactly 2mm, half that 4 from the edge. So there we are, centre line of spindle exactly 2mm from this edge. I'll now move over that 2mm, 0, and then pitch in the amount I need to. Hopefully you can see this. So I've now pitched over 9.2mm, and I've just got to pitch 15mm off the centre line, and then we are ready to start drilling. That's us all set up to start drilling the oilway holes. My long series drills have just arrived, decent quality HSS Cobalt. I'm just going to go to Screwfix, get some more cutting oil, because I'm just about to run out on that. And the last thing you want is to break a drill off inside one of these. So that's what I'll be doing. But we're actually up to nearly 40 minutes of video, so it's a good cut-off point to finish this video up and think about planning the next. So I hope you've enjoyed it. Thank you very much for watching. Keep going with the feedback, it's always extremely welcome, and I look forward to you enjoying the next video. Take care, thank you very much.